Hi, everybody. Here's lecture 23, reading quiz. So now we start to talk about inductors and resistors. We talked previously about resistors and capacitors. Capacitors store energy in the electric field, inductors store energy in the magnetic field. The trade-off between storing energy in the inductor or capacitor and dissipating energy in the resistor gives us the same kind of equations, the exponential decay equations that we got for RC circuits. We get the same circuit behavior as for capacitors for inductors. So question number one, when an inductor and a resistor are connected in series to a constant EMF. So we got a battery, a switch, a resistor, and an inductor. That's a series connection of a battery and a resistor and an inductor. Um, the inductor dissipates energy? No, it stores energy in the electric field. The resistor stores energy in the electric field? No. The correct answer is the current varies exponentially. We're going to see this for an LC circuit. This is an LR circuit, and that's going to make an oscillator. It's going to make a sinusoidal variation. But for this circuit, we have exponential decay. Question number two, inductor and resistor connected in series, same circuit. The EMF, we want to know what the EMF is across the inductor. A voltmeter, we don't use that symbol for a meter, but a voltmeter and an EMF meter are the same kind of thing. Okay. So the correct answer is the inductor follows Faraday's law, so that gives you an EMF that's proportional to the time rate of change of current. Okay. What has, if I ask you what has a EMF proportional to current, well, that would be Ohm's law. Huh? That would be V equals I times R. Epsilon equals V equals IR. That's for a resistor. That's for this one. What would this one be? Well, that's just a silly nonsense question. So I want to know something that gives me something that's proportional to I squared. Well, you know something that's proportional to I squared, but it's for a resistor, and it's not the EMF, it's the power. Huh? Power is I squared R. So there's that. Okay, section 30.3, energy stored in the magnetic field. Here's that comparison I've been trying to drive home to you, that these three components, capacitor, a resistor, and an inductor. Capacitor stores energy in the electric field. An inductor stores energy in the magnetic field. A resistor dissipates energy as I squared R heating loss. That's a power, okay, power, which is energy per unit time. Look at the parallel. We showed for a capacitor that the energy stored in a capacitor is 1/2 CV squared. We're going to show here in today's lecture that the energy stored in an inductor is 1/2 Li squared. Look at the parallel structure. 1/2, 1/2. The quantity, C for the capacitor, L for the inductor. And it's V squared here, and it's I squared here, okay? And it's V here because V makes the electric field. Huh? The electric field is V over D for a capacitor, okay? And the I here makes a magnetic field, okay? And we're going to show that that energy is proportional to that B, okay? So we want to calculate the energy stored in an inductor. The inductor has inductance L, and it produces a magnetic field B. Okay, so current flows into a coil, makes a magnetic field like that. Here's this general relationship for the power in any component. Power is current times voltage. If the voltage is an EMF, that's for an induced Faraday kind of voltage. The voltage is the EMF, so it's current times the EMF. What's the EMF for an inductor? It follows Lenz's law, that's that minus sign there, and follows Faraday's law. The EMF of an inductor is L di dt minus that, okay? And there's a minus sign here because of the work opposing the change. Remember that minus sign in the work energy equation? So here's the power then that we calculated here. That's dW dt. We want the energy. We want U. So that's the work. So I take this equation and solve for this dW. I put dt here and get rid of that. That says dW is the power times dt. That says dW is L di dt times dt. Okay. So tell your calculus teacher to hide his eyes. I'm going to cancel that dt with that dt. So that's L times I times di. Calculus teachers, it's okay. That's formal symbolism. Okay. So that's dW. I want the work. So the W is the integral of dW from 0 to some total final work. That's the integral from 0 to I max. I0, maybe I should put an I0 there. I0, and I'm fixing some typos that are on your handout. That was an L up there. That should be an I0. That should be an I0 there. Okay, so that's integral of that. This thing is a constant. It comes outside there, so that goes there. And then I'm left with integral from 0 to the peak current, I di. That's integral of x to the n dx. Okay, that's x to the n plus 1 over n plus 1. Okay, so if it's 1, that gives me I squared, and the 1/2 comes out there. So there's the work stored in an inductor. Okay, and here's that symmetry that I told you about on the previous page. 1/2 Li squared, 1/2 C V0 squared. Okay, now I'm going to do this real quickly. Huh? We found this for the value of the inductance for a solenoid, and this for the magnetic field of a solenoid. Okay, so if I put the inductor, the inductance for a solenoid in here, and I put I in terms of B here, here's a result we get, which is the work is that. Okay, A times L. Here's the volume of the solenoid. Okay, so that says, this tells me that the energy density, W divided by that volume, is this thing here, which is that. Okay, 1/2 B squared over mu naught. Now I'm sorry, I'm off the screen again. Here's the parallel structure we got for a capacitor. The same parallel structure. U is 1/2, 1/2. The constant for electricity, the constant for magnetism. Here it's in the numerator, here's the denominator, and it's the quantity that's being stored, E squared here and B squared here. Here's what I have to tell you by proof by intimidation. That we did for a very special case for a solenoid. It turns out it's true for any configuration. That's an important result from Maxwell's equation. More about that later. Okay. All right. LR circuits. We're going to do all the same things we did for an LR circuit that we did for an LC circuit. Okay, a battery, a resistor, a switch, and instead of a capacitor here, we're going to put an inductor here. Okay. Now, here's the deal I make with you. We could write down exactly the same sets of equations and solve them the same way we did for capacitors. You didn't like that calculus maybe when we did that. You're not going to like this anymore. It's the same analysis. It's exactly the same. Okay. Here's the picture you get. You get a picture that says the current as a function of time starts at 0 and asymptotes to some final value, V0 over R. Here's the equation, V0 over R, 1 minus e to the minus t over that. Here's the time constant for the rise time of this current. It's L over R. Time constant for a RC circuit was R times C. Remember that? The time that's for an RC circuit. The time constant for an LC circuit is L over R. Now, why does it have that behavior? It has that behavior because of what wants to be held constant for an inductor compared to a capacitor. Let me remind you what we saw for a capacitor. I'm going to start from there. A battery, a resistor, and a capacitor. When we did that, the voltage rose slowly, fast, and asymptoted to some V maximum. Okay, and if we discharge it, it goes like that. Okay. The inductor has the same shape of the curve, but there's a very big difference. Okay. Here we're plotting current as a function of time. Here we're plotting voltage as a function of time. So here's the story. The two curves have the exact same shape, exponential rise and decay, but we're plotting current versus time for L and voltage versus time for C. Why? Very simple, very simple. A capacitor wants to keep V equals a constant. An inductor wants to hold current constant. Energy stored in a capacitor goes like V squared. Energy stored in an inductor goes like the current, I squared. Okay. Conservation of energy doesn't want this to change abruptly, doesn't want that to change abruptly. Okay. Okay, we're going to do the Colorado p-hat thing here in a minute, but let me walk you through the answer to this question for a qualitative circuit. Here's again the circuit: a battery, a switch, a resistor, an inductor, R, L, V0, and the switch. Okay. And this question asks you what happens to the steady state value of the current, that's it for t equals 0, okay, and what happens to the rise time. Okay. Let me solve this with you two different ways, one purely mathematically and one physically. Here's the result we got on the previous page. If you're a mathematician, then you like to write this equation: I is V0 over R, 1 minus E minus T over tau for the LC circuit. Okay. Tau LC was L over R. Okay. So what happens here? Okay. What happens here is initially this current wants to flow through the inductor, but if there's a current flow here, the magnetic field wants to change. Okay. Faraday's law in the previous lecture says I don't want the flux to change through there. Okay. And the way I make the flux not change here is at t equals 0 for this to keep the current from flowing. Okay. And that will make the current be 0 to begin with. Okay. That's the shape of this curve here, 0 voltage at t equals 0. Okay. As time goes on, the energy starts to get stored in the magnetic field, and finally this voltage becomes equal to that voltage. Okay. It goes to 0, and all the current flows through that resistor. In other words, as t goes to infinity, this term goes away, and the current is V0 over R. So here's the steady state current. I steady state, that is I as t goes to infinity, is just V0 over R. This problem asks, what's the I steady state if I make the resistor a higher resistance? Okay. If I make the resistance higher, then the initial current would be smaller. Okay, so that's this term here. It would take more or less time to go there, more or less time to go there. Okay, so the resistor with the higher resistance makes this smaller. If it makes it smaller, that's this part here. What about the time dependence? Okay, the time constant LC for a smaller resistance gets shorter, so it takes it less time to get there. So the answer is it would take less time to get there. So the answer is number C. Okay. Man, we're up to 14 minutes. Okay. Here's LC circuits. I'd like you to read this on your own. It makes a simple harmonic oscillator. I'm going to try at the end of this to show you that behavior just with the Colorado p-hat thing. Okay, so let me jump right away then to the Colorado p-hat